So before, I mean, just short. Yes. So before I introduce you, I just would like to say some words in Portuguese about this course. So só para colocar o seguinte, quem está assistindo o nosso curso, são as atividades de verão, mas as aulas do SAM, elas vão ficar como parte complementar do nosso curso de campos quânticos. Então, quem estava fazendo campos quânticos no segundo semestre, nós trabalhamos uma série de assuntos e aí o SAM entra agora para cobrir realmente a parte de ordens superiores. Então, quando a gente colocar na rede o curso que estiver disponibilizado no servidor, as aulas que o SAM vai dar vão ser complementares ao curso de campos quânticos, certo? Só para avisar para quem está seguindo o curso. So, it's our great pleasure to introduce you Professor Sam Friot from France, from Paris. So Sam very kindly is coming with French money, not Brazilian money, but very kindly he accepted to teach this course in class. So this course will be very good for you people, for you who are following courses on quantum fields. So he's going to show many technical details, so he's expert in this subject. You work with Rafael, so in this course here, quantum field, several times we referred Professor De Rafael's works on T-2 for the electron, for the moon. So somehow you are going to drink the water from the spring, because Professor Friot is a co-worker of Professor De Rafael. So somehow Professor De Rafael's school is here teaching you and teach people in general some nice topics about higher order computation in QED. So Sam, thank you so much indeed, okay? And I hope everybody here enjoys your lectures.
Thank you very much for giving me the opportunity to give these lectures. I'm very happy to be here. So they concern higher order QED calculations, since it is a very wide subject, and because QED is a known QFT, that's number in this field, and we will spend a few hours together. So I had to make a choice, and the choice that I will concentrate mainly on the anomalous magnetic moments of charged leptons in these lectures. So, we will consider the electron, the muon, and the tau. So the reason for this choice is that historically it was an important test for the QED perturbative approach, okay, and the normalization procedure. And the normalization, since it is in this context that the first tool, the normalization, the normalized calculation has been performed in the 50s, in 1915. Then, after decades, it became test of this compound model. Nowadays, this is the place where perturbative calculations go deep and deep in the perturbative expansion. Since we are now at the 5 root level in QED, which is really impressive, you have to compute more than 13,000 of Feynman diagrams, which is something. Normalized. And more importantly, in fact, today, it is the most compelling indicator of physics beyond the standard model. The most convincing indicator of beyond standard model physics today. Since we have now the 3 sigma deviation of the mirror, and there are very good reasons to think that in the few years sigma or even more, because there is an experiment that will begin soon. And they plan to reduce the uncertainty by a 4 factor. It will be enough even if the standard model predictions stay their level today for 5 standard deviation. And this will be done, we hope, before 2020. So only a few years to wait. Therefore, it's important for students to know at least minimal things about this subject, I think. This is why I chose to speak about this other subjects. But I will mention a few things about another very interesting quantity, the electric moment of the same charge difference. But only a few words because I am not working on this key. Moreover, in quantum electrodynamics there are no contributions, and in the standard model we begin at the 3 level for a 0 contribution, like 40. So it's extremely difficult.
So the first contribution to the electric dipole moment that is a 3 loops.
Yes.
First non-zero.
Well, it is 0 in fact. Then you have to go a bit. But before there are no Feynman diagrams.
At 3 loops it cancels. It is zero.
Yes, it cancels. At least, well, when in the original paper when neutrinos were massless, in fact, so now things have perhaps changed, but due to the small mass of the neutrinos, this is even smaller than what we will find at 3 loop level within the standard model. So QED contribution is and standard model. Okay. So the lecture will be mainly divided in 2 parts. The first one will be the state of the art of the G-2 of charge difference today, but we know experimentally and theoretically. So we'll give a lot of numbers. And then the second part will concern loop calculations. So the anomalous magnetic moment is also called the anomaly. Okay, so it's short of G-2. And then loop calculations in this context in QED. Okay, we warm up with the one loop results given by Schwinger that you already know and perhaps computed. Then we do full two-loop calculation of the mass dependent contributions. And then, if we have time, because I don't know how much time it would take to write this in the black hole, I hope to be able to present you some free calculation. And I will give mostly all details for the calculations, since I think it's important for students to have everything written and to compute with me. In fact, to help me, because it's not easy to compute on a blackboard without doing mistakes. I very probably will do some mistakes, so I will have all your attention and help. Follow the calculation detail to help me. Okay. And somewhere I will try to say a few words about the electric dipole model. So in the context of quantum theory, both quantities that we are interested in, electric dipole dipole moment and value, may be obtained from the matrix element. I consider minus charge vectors. Okay. So where this is electromagnetic current, in the standard model. So we have charge vectors, parts, electronic pH bosons. And this is equal to this, where in fact we have a mu is this object. Okay. Now, the general structure of this may be derived and reads as follows. We have a mu times F1 Q squared. Q squared is the here, plus sigma like 2 and is the mass of the vector times F2 squared minus the same object multiplied by M15 times a third form factor plus Q squared gamma 2 minus 2m L Q u gamma 5 F4 of Q squared. So the Fi are form factors. Okay. Okay, you may derive this by Lorentz invariance, the Dirac equation, and the conservation of current. This is the most general way to decompose this object. Now, F1 is called the Dirac form factor, and it's related to the electric charge. F2 to the power E1, or E1, and it is related to the anomaly. F3 is different from 0 if parity and time production are broken by anything. And F4 is the anapole moment. I forgot to say that on F3 you have the electric dipole moment. Okay, so you see that it implies parity and time. Violated, which means that in QED it's not possible to have contributions. And here, this is different from 0 if parity okay, so the quantity we are interested in is subject, and it is also related to the spin magnetic moment of the spin 1/2 charge particle by this formula. Where S is the speed, J is the gyromagnetic factor, J equal 2 times 1 plus 8 ampere. This is, in fact, the prediction from Dirac's Dirac theory, Dirac equation. And these are the deviations, small numbers, induced by quantum fluctuations. This is what we want to compute. Okay? But before computing it, in QED, I will present the actual experimental and theoretical situation nowadays, today. We begin with the electron. Okay. So the first measurement of the anomaly has been done in 1947 by the two physicists. Well, the head Kush Fourier. This is Fils. And they found this result. that we have an error on the last number. Okay? And in terms of precision level, if you divide this by this, you find 4.2% of precision. For this, we got the Nobel Prize in 19. In 1955. Okay, and in the introduction speech of the Nobel Prize this year, they said this is for this precise determination of the magnetic moment, analyze from the moment of the electromagnetic moment of the electron. Okay. Now, just one up. You have the famous calculation by Schwinger. Okay. Continue to line next at 1 loop. So this is Schwinger. His head. And in 1965, he got the Nobel Prize. Not only for this, but in the speech, they tell mainly a few things and the fact that he computed and numerous for this calculation. This. So this was an important quantity, of course, because it allowed for the beginning of QED, perturbative approach to be really accepted in the physics community. Now, today, so this was a long time ago. Today, what is the situation? This is, of course, the most precisely determined quantity, perhaps in all the physics. So we have astonishing precision. I don't know it by heart. This is 159. This is 52. No, it's 7. Okay, so the precision level now is 0.01. Okay, so this is equivalent to, in fact, 0.4 parts per billion. Just to give an idea of the size of this error compared to the number that is measured, it's like if you knew the distance between the top of the Eiffel Tower and the top of the head of the Corcovado with a precision of 2.5 millimeters. Okay? So, we know it quite well. Okay? It's probably the best most precisely measured and calculate it also. Because we will see the theoretical result just after. In all physics, probably. Now, the theoretical result. Yes, I forgot to say there are no other colors. No. I wanted to mention the guys who did the last measurement. This is Gabriel C. Ali. This is RevNet. Project. 2008. Okay. So this is, and now theoretically we have this result. And the only difference comes here. You have 1, 7, 8. Right? Okay? This is Kinoshita. Then, in this RevNet, now, this has been obtained with some alpha value, which comes from another experiment, and which is the second best.
And this result by Kinoshita, that is the 5-degree result.
Yes, but you also take strong interactions.
Okay. And all the standard law.
Yes, this is. I cite the last paper because it has been evaluated, but it's not exactly the last paper. There is another that mentioned after. This is the Raphael paper.
Okay. Thank you.
Yes, it takes into account 5 groups or actions that have been computed, but not completely in the sense that they do not care about tau loops inside the calculation at the 5 loop level. Okay, so I wanted to give the alpha value that has been taken to obtain this value. It is this. I'm sorry, I do not know by heart. Okay. The precision is, yes, I forgot also to say it. Precision 0.66 per billion. Okay? And this is the same curve. So this measurement comes from the h over m RD, which is Planck constant, over the mass of the rubidium atom. Yes. and this maybe obtained in co-data. Then plus Pushenia. Okay, so if you want, you may also compare the theoretical calculation to the experimental one to get the value of alpha, of course. Okay, and then you take the best evaluation of alpha. The second best is this one. But to make a prediction, it's better to use it. Okay. So, if I summarize, in 1948, we have that a electron theoretical equal a electron QED one loop. And now, theoretical equal a QED 5 loops plus a strong hadronic plus the weak contributions, and this number is 1.685 times 10 to the power minus 12. So this means that it enters here 165 85. Okay, and the weak contributions, they are 0.02975 10 to the minus 12, which means that they arrive here. Yes. So we see that in the case of the electron, we are sensitive to the hadronic contributions, but on the weak contributions, it's still too small. But in the case of the muon, which is more interesting, why? Well, more interesting, not really, but because this is very interesting to be able to get alpha with great precision, etc. But in the muon case, it's interesting because the muon is much heavier than the electron, and its lifetime is very short. So it is a problem for experiments, but since it is heavier, it's a way, in fact, to be more sensitive to other interactions, like strong interactions, electroweak interactions, and beyond standard model. Okay, so what is the situation for the muon? The first measurement came in 1960. It is it has been done by Garvin et al. In Israel. Okay. the number following. Then theoretically, the full the calculation that was known at the time of the measurement was a two-loop calculation in quantum dynamics, which gave the following result. This is equal, in fact, to the electron case, because in quantum dynamics you have two types of contributions: the mass independent contributions and the mass dependent. So this is the number of the mass independent contributions that were calculated in 1950, but then you add something, I think I will. You add the contribution of this kind of diagrams, okay, where the electron is not the same. So if you have mu here, you have an electron here. Not the tau, because it was not discovered at this time, and because it's really suppressed also, in fact. So if you add this, you get, well, this contribution is in fact 0.00059. Then you get the contribution so you have to add both, in fact. Okay? To obtain the result. I cite Sommerfeld for the QED mass independent. This is Anna's physics, New York, 5/26/1958. In fact, the result given in 1950 by Carl Plus and Kroll was wrong. They renormalized well, and in this sense it was very important for QED, but they gave the wrong result. And 7 or 8 years later, they corrected the error and added this quantity to get the result. This is by Peterman in Fitzgerald 1957, and also I don't correct the name, and Ishman. Israel 1957 also. Now, concerning the electron, corresponding to this, with a Luhr, this has been first calculated by Bernstein and Dalton. 1969. Okay. So now the situation in today. So in 2014, the numbers are the following. Zero, 599.63, which means that we have only a precision of 0.54 per million compared to the electron where it was billions. Of course, it's much less precise, but since you have a huge difference between the masses, in fact, it doesn't matter because this level of precision is already sufficient to have better insight for other interactions than QED. And the problem comes in the theory with the evaluation of these contributions, probably the strong interactions. So RS. So this is Bennett. This is the experiment 8.21. And his red okay. Theoretically, we have two values. Now, you have this value (91802). Okay, 803. Then this. Yes, plus or minus 49. Okay. And the other, the same number, but at the end of 28. And the error is 50. So it comes from two analyses of the strong leading hadronic vacuum polarization, strong interaction contribution. So this is David. I put David. This is Ajivara. Now this leads to 3.6 standard deviation. Okay, because there is a difference. Quite important. And this only 3.3. Okay, these numbers are taken from last paper with Rafael. This is well, we can just before say this. Difference between theory and experiment is these two numbers. And this is here that we have the standard deviation. from the last paper of the Raphael, which is Bloom. Archive 1311. Now, what is important is that the aim at Fermilab with the experiment that we cited E989 they have the aim to get from this 63 only 16. Number, we will try to draw this one. This array.
This blank paper must be a head pH or a physics pH?
This is archive. Now, you don't have the difference between pH
between after brackets, that's maybe head pH.
I don't think so. If you, inside archive, if you do that, yes, perhaps you're right. This is pH.
Okay, pH, no?
Okay.
And also, in these two results by Navier and Hanjulara,
yes.
They did exactly the same thing, or maybe someone concluded with QED or QCD corrections. What's the reason for the differences? Just statistical.
An analysis of the experimental cross-section of E plus E minus in 200s. Because in the case of hadronic vacuum polarization, you can avoid computing them from QCD. By a trick using a dispersion relation, you use the imaginary part of the polarization that you can express in terms of the cross-section and use experimental measurement of this cross-section. And they differ, these two approaches, they differ by doing the calculation with this cross-section. But these are not full theoretical results, because in QCD you have non-perturbative effects that are, of course, present in this anomaly, in this fashion. Okay, so with this, we will have, if we stay with the same numbers, we have 5 sigma. So, new physics. Okay? But probably there will be some refinements here. And we can hope for a 7-8 sigma deviation. Okay? So it would be nice with LHC to have to. So this is why it's an interesting subject. We will know in a few years. Well, there could be some mistakes, because there are things inside the hadronic contributions that are completely model dependent. We will see later that you cannot avoid to compute, because you cannot relate them to a measure like here with the cross-section E plus E minus to atoms. These lie contributions. So I summarize. in 1960, we had a new theoretical equal to a new QED. Two loops. Without the tau contributions, of course, because it was not discovered. And today, we have a new theoretical, which is equal to a new QED 5 loop. Plus a new hadronic plus a new weak. Well, these 5 new contributions do not contain tau loops because they are suppressed. And these two numbers that leap, and the other one, cool. I pulled that. It's not that you did the whole thing because there are also this model dependent contribution inside. Plus minus, that means did only the lowest order atomic algebra. Okay, the weak contributions. They are the following. So, this means that we are here. We are here for the weak and here for here for the form. Okay. So what they need is to feel the weak interactions. Okay. And the main uncertainties come from this in the whole calculation. This is the main point where theoretical physicists have to work a lot. So, if you want to compare this contribution with those of in the electron case, you would find that approximately they are equal to the same value as the ratio of the square mass. Okay? This means that due to its mass, the muon is 43,000 times more sensitive to atomic physics than the electron. So, you may think that the tau, which is even heavier than the muon, would be better to do the codes of new physics. This is the case, of course. The problem is that it has very, very short lifetime and that it cannot be measured with a good precision at all. So, let's talk about tau. Just recall for the muon the human lifetime. 2.2 10⁻⁶ and the mass in the case of the tau, you have tau. So this is 2.9. Times 10⁻³ and the mass of the tau is equal to this. Therefore, the ratio of the square mass, this is something like this. Okay, so it will be very, very interesting to be able to measure the anomaly of the tau with a good precision. Unfortunately, because of this, which is due to the fact that it's a very, very heavy lepton, which can decay into hadrons. Okay, we are not able to perform nice measurement of the anomaly for the tau. So this is the situation. We have this number. This is not even directly measured. This is deduced from an experiment. And this is 95% confidence level. This is Delphi collaboration. European physics. Okay. Now the theoretical part today is the following number. I cite last paper of Raphael. No, sorry. It's not with Raphael. It's Spacera. We did some work on the tau. Sorry for writing everything, but I think there will be something based things on. The precision in this case is 42 per million. And if I summarize, I have a tau equal to 8 tau QED and 3 loops and not 5 because there are no experimental things to compare with, plus 8 tau hadronic, which is around 350 plus or minus 5 10⁻⁸. You see the difference between this and this. And also the weak contributions. The weak, I never said that it is at the 2-loop level that it has been computed, and it is already hard because at the 2-loop level you have already 1600 diagrams, Feynman diagrams to compute, so it's not easy. this is 47.4 10 to the minus 8. So there is a hope to measure the anomaly of tau in the near future, but with a precision of 10 to the minus 3, which is not so good. And yes, from the top to 10 minus 9. We will obtain 8 with 10 to minus 3 precision level. This is out. Okay? Okay, so now I will detail a bit more all these contributions. Okay? The QED contributions, hydraulic contribution, electronic contributions, and then we will do some calculations in QED. So, I said that in QED, we know the anomalous magnetic moment of the electron pendulum at the 5 loop level. Let's detail a bit more. So we saw in the beginning that we come from this kind of diagrams. Okay. And in QED, this is at lowest order Dirac 3-level result. Plus, I can move the following quantum correction, plus I have to do the corrections in this, which comes in this kind of diagram, plus this one, plus this one, plus not so much, so I'm really doing that. So you have the symmetric parts. Also add here. This is the mass dependent contribution we always spoke about. Plus, well, if you consider the same electron in the loop, there are no mass dependency because they have also to be computed in the mass independent contributions. Plus, which one is missing? 7 from 4, 6, 7. So everyone is here. At the two level, you only have 7 diagrams to compute. And this one has to be computed with electron, for instance, but also electron tau, electron mu. This is 9. Compared to the weak case, where you have, I said, more than 1,000 diagrams already at this level. At the 3-loop level, you have, okay, correction to this, plus, I will not go everything, but there are 72 diagrams. But only a few that are coming at this level. interesting one is this one, the light. Okay. Plus another which is interesting, auto suppressed, plus all the correction tools. Okay. So you have 72 diagrams. So this vertex does not contain only F2 as we saw. You have to project on F2 to obtain the value of the element. And in QED, the anomaly is given by this formula. Okay. Where alpha over pi, just to say, is around 1/12. Okay, this is the expansion parameter. And the AL to L bar divided in 4 parts. The A1 to L, which does not depend on anything, the mass independent contribution, plus A2. So there I will yes, N over N prime with N. Well, let's see like this. Plus A3, which is the same, but with L second and 1 prime. Okay, here if you have the direction, you have the real in here and the tau here. Plus A4 and with both ratios. Like this. Okay, so if I match this formula to the finite diagrams, this will contribute to this, for instance. This one also, this time. But this one will contribute to this. Or N to this with another vector, and this one will contribute also to this. You have 3 diagrams here, I said. Okay? This one, that begin at 3 level, will contribute to this. Is with A4 with N equal 0, 0 is the Dirac level, okay? With N equal 1 and N equal 2, A4 equals 0, okay? So, I managed to explain all the numbers for these quantities, but I don't know if it's necessary. In fact, I have all the numbers into 5 groups. I don't know if it's necessary to go into some.
For computing the electroweak corrections,
yes,
and for these higher loops, for example, 2 loops, we may have exchange of Higgs boson inside the loop. And so
even at one loop.
Even in the one loop, no?
Yes.
So did people consider the new measured mass of the Higgs, let's say this 125, which these values which we are getting from QED or from electroweak, they already take into consideration this 125 mass?
Yes.
I see.
Yes.
The most recent result. Because previously, let's say, the Higgs mass was a parameter.
Yes.
And we had bounds. But now we know the precise mass.
I think so. I have no paper in mind, but...
I see. Okay. Thank you.
Okay, so... I think perhaps it's not necessary to go into all the details for each of these contributions for each lecture. Right.
Yeah.
Perhaps it's a bit boring. This is interesting because you can compare the sizes of the contributions for each chapter to see that, of course, the mass dependent contributions for the lessons are very different. It gives different number for the total contribution, but I think perhaps it's better to avoid it. So I will only say that, yes. N equal this. Okay, because 0 is a Dirac result, but it's not in the anomaly, it's outside the anomaly. So N equal 1. You have only one diagram that gave this Schlinger result. N equals 2, you have 7 plus 2 if you want diagrams. I count here the mass dependent contribution. And as I said here, A2 and A3 are 0 and A4. Here, A4, that is 0. Yes. So, N equal 3 about 72 diagrams. All contributions are 0. I will not pick the numbers. You can find all the numbers for the N equal 2 case in Aula. And not only the second order, but all the cases. Yoshida team. This is the last. Okay. And for the tab, you have to go to, because this is for electrons and mirrors, for the tab you have to go to Casera. Red. 207. So for what I said here, to find the numbers, because I will not write everything, otherwise you lose what you find.